Okay, we're looking at practice test 2, the second half, problem number 1. As I stated before, if you want to get the best out of these problems, pause the video whenever I ask a question or ask you to do a calculation and try your hand at it. Then continue the video. We have a block incident on a bump at speed v. As it goes over the bump, it rises 0.5 meter. It is on a circle. The bump has a circle of radius 2 meters. The question is, what is the maximum speed the block can have so that it will not leave the surface? We will consider the block, the earth, and the surface as all part of the system. Okay. Let's look at the velocity at the top. In this case, we want to use conservation of energy because that'll get us what the velocity is at the top. As the object goes up, it gains potential energy and loses kinetic energy. So our conservation of energy equation states that the change in kinetic energy plus the change in potential energy must equal 0. We know what the initial velocity is, that's just v. The final velocity is vt for v at top. And then the gain in potential energy, of course, is mgh. That's mg times 0.5. Using a little bit of algebra, we can then solve for the velocity at the top in terms of the initial velocity, because it is this initial velocity right here that we're going to want to solve for ultimately. What are the forces acting on the block at the top of the bump? Okay, here we have to go back to Newton's second law and identify the forces. So go ahead and draw a free body diagram. Of course, we have the normal force acting on the block and gravity. And since it's moving in a circle, we have a centripetal acceleration toward the center of the circle, and that'll be in the downward direction. What is Newton's second law for the forces acting on the object? And of course, the normal force minus the gravitational force will equal to the centripetal force, also in the minus y direction. What is the normal force just as the block leaves the surface? Or I can ask the question, once the block has left the surface, is there a normal force? Of course, normal force is 0 just as it's leaving the surface, which leaves this equation here, resulting in this equation here, that the force of gravity is just equal to the centripetal force. And that leaves, we can get rid of the m's, and we have that g, the gravitational acceleration, is just equal to the centripetal acceleration. All right. How is the centripetal acceleration related to the velocity at the top? And of course, we have that centripetal acceleration is the velocity at the top squared divided by the radius r, and that must be equal to g. And of course, we can come over here. We have my VT relationship here, and that can come over here and substitute right into here. And now we're in a position to solve for v squared. So solve for it. and we find that V is equal to square root of the G times R minus 2GH. And that equates to 5.42 meters per second as my velocity V here. Original problem we did where we did not take into account 0.5 meter, where I believe we got something like 4.4 meters per second. End of problem.